Good afternoon, all, and warm welcome to Best Practice Meets 2021's track session on crypto enabling digitization and guaranteeing privacy, searchable encryption, homomorphic encryption, and confidential computing. In this digital and interconnected era, businesses are increasingly transacting directly with the customers, which means they are collecting a growing amount of personal data. Digitization operations gives business access to data analytics that can help them discover new insight about the customer and behaviors automatically without having to ask explicit questions. This data is being stored on the cloud where it's vulnerable to cyber attacks from criminals who are looking to convert data into money through either ransomware that holds data for ransom, identity theft, and selling files on black market, and many more unimaginable ways to trouble people. Experts anticipate that over 75 billion, ranging from smartphones and cars to industrial machines, will be connected by the year 2025. Digitization undoubtedly produces great opportunities. More safety on the roads, for example, thanks to self driving vehicles or machines that take over tedious tasks, communicating directly with each other, and even longer and healthier lives for us, thanks to telemedicine applications and new research result based on a big data analytics. One of the biggest challenges business is facing during this time of digital disruption is in building trust among clients as an organization that protects privacy while also providing a seamless online experience. The technologies that guarantee data privacy in today's age are homomorphic encryption, searchable encryption, confidential computing. For storing data and outsourcing its computation, end users like enterprises and individuals are increasingly getting cloud service provider on board instead of handling the data themselves. This is because cloud service provider services at an affordable cost and with much ease of use. One major challenge for user of cloud services, however, is preserving the privacy and confidentiality of the data stored on the cloud, which is why the data is encrypted before upload. However, the CSP has to decrypt the data to enable the perform computation on it. This reveals the data to the CSP, causing significant privacy concern for end user. This is especially relevant given the current background of the privacy concern about third-party data and regulation such as GDPR that are meant to ensure data privacy. Cisco report on the Global Cloud Index suggests that 94% of the workload and computing instances are processed by cloud data centers, and of that 70% are managed by public cloud. Alarmingly, users don't have control over their data and naturally concerned about data privacy. Furthermore, data is often exposed to breaches where sensitive customer information is accessed in an unauthorized manner. Customers often risk privacy of their data in exchange for services from the CSP. And while users can encrypt the data and store it on the cloud for the purpose of confidentiality, it limits any kind of data processing. Therefore, the usual encryption is limited to data storage alone and does not allow for any meaningful computation. To enable computation while guaranteeing the data privacy, researchers are focusing on privacy-enabled computation. One of the promising approach in this direction is the use of cryptographic paradigm called homomorphic encryption. HE is often considered the holy grail of cryptography as it enables privacy preserving computation in almost all possible scenarios. Some of the use cases of HE are private search, encryption, encrypted database, and many more. Another very promising area is searchable encryption. SE is defined as searching for an encrypted data located on untrusted server or a cloud without the server learning anything from the data. In 2000, Song proposed the idea of SE scheme which solves the issue of searching encrypted data on the cloud. Another upcoming encryption field and attraction of the researcher is confidential computing. Today, data is often encrypted at rest in storage and is transit across the network, but not while in use in memory. Additionally, the ability to protect data and code while it is in use is limited in conventional computing infrastructure. Organizations that handle sensitive data such as Personally identifiable information, financial data, or health information need to mitigate threats that target the confidentiality and integrity of either the application or data in system memory. Confidential computing protects data in use of performing computation in hardware-based trusted execution environment. This secure and isolated environment prevent unauthorized access or modification of application and data while they are in use, thereby increasing the security level of organizations that manage sensitive and regulated data. As a threat vector against network and storage devices are increasingly thought by the protection that applies to the data in transit and at rest. Attackers have shifted to target data in use. The industry witnessed several high-profile memory scrapping, such as target breach, the CPU side channel attack, and having dramatically increased attention to this third state, as well as several high-profile attacks involving malware injection, such as Triton attack and Ukraine Power Green attack. Let's see what our experts talk about all this week. To deep dive into the area, let's invite our first guest for the session, Ms. Zenia Bogomolek, Information Security Specialist and CEO, Quant Security and Coding Germany. Welcome, Zenia, to BPM 2021. And thank you for joining us.
Thank you very much. I'm happy to be here.
So over to you.
Thanks. So I will more talk from a general perspective about the importance of cryptography in the context of information security and information risk. And for this, I prepared some slides. Okay. Can you see the slides now? Okay, so we are a small startup in Germany, and we work in information security consulting, mostly in the financial sector, but we also focus on algorithmic topics, especially cryptographic topics. So why is it so important for us to focus on this topic, cryptography? Because from our point of view, it has a very special meaning in information security. If we are looking at a very basic scheme about companies interacting with each other, we have lots of security measures as long as data is on the infrastructure of the company itself, like security information event monitoring, intrusion detection system, intrusion prevention system, malware protection, access controls, and so on. So, of course, here cryptography also is very important for all the topics which were previously mentioned. But when it comes to the transfer of data, the pure communication part, cryptography is the only protection we do have in place. So that's why we consider it especially sensitive. In the last years, we had a lot of new high-performance attack vectors occurring. And amongst them, if we look at the stack of cryptography from a process perspective, like it starts all with mathematics for algorithms, then the implementation of algorithms affects computer science, then we have implementation, system integration, application integration, networks, administration, then the management of all these and the users. So we have high complexity in end-to-end processes of applied cryptography. And the threats which apply most on the lower layers of this crypto stack, which I call it, is once increasing performance of binary technologies. Then we have new mathematical solutions for problems which are the base of currently used cryptography. And then we have the quantum computing, which also was mentioned in previous talks already, which will require completely new algorithms, post-quantum secure algorithms for cryptography. So if you want to have an overview on the high-performance attack vectors, we have the current threats, password and cryptography cracking tools like Hashcat and similar tools. They are open source, they are available for anyone, and very high performing computing toys which even run very well on normal computers. Then we have these aggregated computing resources and parallelization attack. Like booking a lot of Azure instances and running attack processes on several machines has become very easy and not even expensive, because you can just book them for a day, for example. And then we also have new mathematical solutions affecting parameters and configuration of classical crypto. One example in the last years was that some parameters of Diffie-Hellman were affected by a new solution for discrete logarithms. Here, the countermeasures, my recommendation is regularly check RFCs, request for comments, and recommendations of official data protection and information security institutes for once, of course, the choice of algorithms, then the key length, but also algorithm parameter configuration. And update your systems accordingly in alignment with depending parties. Then near future threats are evolving quantum computing technologies, which will make it possible to decrypt data which is encrypted by Diffie-Hellman, RSA, and elliptic curves. The timeline for the technologies being strong enough was guessed by IBM, could be even 2023. So, of course, we need to think that not everyone can buy such a computer and make this kind of attacks. But in the last year, especially, that there were great progress in the development of quantum computing technologies. And we got several signs from experts that we need to really start implementing post-quantum security in the wider sense. So here we have countermeasures, use new post-quantum crypto algorithms for binary technologies. A previous member has talked about the NIST standardization already. Yes, of course, as soon as they are done with the standardization process, these new algorithms will be integrated to official crypto libraries like OpenSSL and other libraries. But we also have the possibility to enable post-quantum security earlier for very sensitive topics. Then homomorphic encryption, of which it was very well outlined what kind of advantages it offers compared to other encryption methods. This should also be post-quantum secure because they are not based on the mathematical principles which are prone to quantum computer attacks. And then we also have quantum communication technologies, which will require new quantum hardware and is more expensive. But these projects are also being set up more and more. And yeah, it will be an interesting future with our new technologies. So for me, it is very important to give you a very short introduction on how you can think of where does it make sense to apply these new methods first. Because as an information security consultant, I know you go to a company, they have maybe, let's say, 5,000 digital assets, and where to begin even with new innovative technologies. It's not so easy to identify. So first, I just want to tell you, your business process and the respective IT systems are your assets. So that's the thing which we want to protect. And the data which is being processed by those assets is, of course, also a part of the asset. According to ISO 27005, we have two primary assets, which are end-to-end business processes and data. And the IT assets or the systems are the supporting assets for the primary assets. So the first step would be perform a CIA rating on your systems, which will indicate the protection need of the respective systems. And from my point of view, the best candidates for near-time transition to homomorphic encryption would be the ones with high confidentiality and integrity classification and low availability rating. Why? Because the low availability rating plays well with the performance, the slower performance, which we still have with some of these methods. Yeah. So the best candidates for post-quantum cryptography are the ones which process data which needs to remain confidential for many years in the future. And then, as a second step, if you have identified those candidates, I would recommend to perform an information risk assessment to consider threats versus the system protection need. This will help you to determine which new cryptography you might want to apply to which system. And a guide for conduction of information risk assessments can be found on several pages in the internet, amongst them also the NIST, but I'm sure you also have very good guidance on Indian pages. Yeah, so that was my short talk, and my conclusion is stay aware about upcoming threats and solutions and introduce swift crypto patch processes, because we might be facing quickly occurring new threats in the next years. So thank you, and you will find these slides on our homepage on the page published in the section Talks, Presentations at Conferences and Events.
So yeah, wonderful, wonderful, Zinia, and thank you so much for an excellent presentation. And
you're welcome.
And thank you so much. So we will join again back on a stage after Ayantika's session. So
Okay.
I'll request. So to discuss more about these areas, let's have our second guest, Dr. Ayantika Chatterjee, Assistant Professor, IIT Kharagpur. Can we have Dr. Ayantika on stage, please?
Hello, welcome to this talk on welcome to this presentation on a few crypto solutions for privacy preserving digitization. So I'm Ayantika from Indian Institute of Technology, Kharagpur. So while talking about digitization and its privacy preserving steps, we can start with few data leakages, few data hacks that we have observed in recent past in different from different organizations, and few IT big names like Yahoo, Microsoft, Apply Cloud, and also other big companies like Marriott, eBay, Uber. So all these names are associated with this. So the list is quite big and not, of course, exhaustive. And if we just take the recent data from 2021, just the first half of 2021, so there also the list, the news of this data hacks, data leakage is quite big. So when we are thinking about digitization, of course, this is a big issue, and we have to talk on that. So what is the solution? Of course, the direct solution can be when we are moving to store data for this, that is a output of this digitization, we can store them in some encrypted way. And when we talk about this cloud computing, cloud platforms, there, of course, encryption is a solution. But if we go for traditional encryption, the problem is that we have to decrypt back the data again while computing on them. Otherwise, if you want to just do a simple search on that encrypted data, cloud will give you back the whole file and tell you, you search yourself because I do not have the secret key. So for that, and on the basis of that, this literature of encrypted data, computation on encrypted data is developing. And the few solutions here we have, the starting from privacy preserving encryption, then order revealing encryption, then fully homomorphic encryption. So these options are starting from very low security but high performance to very high security, high flexibility, but with some performance, I mean a huge performance issue. So when we talk about the few names like property preserving encryption or randomized encryption based compute options to compute on encrypted data, there is always a trade-off between the security and efficiency. Somehow you can leak some information. There are some known some known attacks on such encryption schemes. So from the aspect of security, they are not fully secure, or there are some leakages possible. Whereas if we come to this searchable symmetric encryption kind of solution, there we can see, of course, security is not a big issue. It is secure, but we are limited in terms of what kind of operations, what kind of applications we can support. So finally, the holy grail of cryptography that we consider, that is a fully homomorphic encryption, which promises to have the support of arbitrary operations. You can perform arbitrary operations on encrypted data, but of course that comes with the cost of performance, first of all, and the second, the cost of ciphertext expansion. So whenever you are thinking of developing any application based on this FHE fully homomorphic encryption scheme, you need some options. You need some options to support huge ciphertext expansion. That means huge amount of memory requirement. So before going to the what type of applications we could support in this direction, we first talk a bit about what we mean by homomorphic. So homomorphy is defined in this way: if we are considering two groups like G and H, and a homomorphism from G to H can be considered as a function F, where if we are performing any operations on the elements of, let's say, on the group G, G1 and G2, let's consider they are the elements coming from group G, we are performing some operation on them, and then we are applying this function F. It is equivalent to applying that function F on that elements G1 and G2 first, then performing some operation. That means if we can map this function to encryption function, of course, we can think that it is equivalent to saying that we are performing some encryption on the cloud data. We are performing some encryption on client data, and then we are performing some operation. It is same as first we are encrypting them and then performing some equivalent operation. So basically, homomorphy gives us that support, that flexibility to perform on encrypted data. But where is the magic when we talk about this homomorphic scheme as this solution to this computing on this encrypted domain? Where is the magic lies? If we just see a simple example this way, let's say consider it as a ciphertext. As in this form, you can see in this the left side third fourth line that C is equal to PQ plus 2R plus M. So where M is my plain text and P is my secret key, Q and R they are some random numbers where Q is considered to be very large. So there is some proof if you can consider C1 and C2, two different ciphertexts of this structure, and then if you perform some addition and multiplication. In the right hand side, you can see if we expand the expression after doing this addition on the ciphertext, there is some term related to this random number, random R1 and R2. So these terms, for the time being, let's consider we can term them as error term. And if we closely follow the expression and our decryption algorithm, then if we can keep this random number related terms within a certain threshold, then we can confirm homomorphy. That means that's why whenever we talk about homomorphic scheme, there is a concept of controlling the noise. But the thing is that how can you control the noise? That means some associated module. It varies depending on the library. It varies depending on the scheme what you are mentioning. There is some terms we call like retrieve, like bootstrapping, in the domain of homomorphic scheme, which is mainly responsible to keep this noise within a certain threshold, or it is helping, this bootstrapping schemes helps us to generate new ciphertext of lower noise or noises within some errors within a certain threshold. Now the background math is too in depth, so I cannot explain that as of now, but just the key point is that this recryption or bootstrapping support present in this homomorphic scheme is basically the boon to this encryption, homomorphic encryption scheme, because this is the main reason why one simple encryption scheme can be homomorphic. On the other hand, this is the curse, because due to the presence of these operations, this noise handling module, to support this type of operation, this ciphertext expansion is there, performance degradation is there. So whenever we talk about this homomorphic encryption related operations applications, we talk it as a, oh my god, this is the performance is too much. I mean, it is a huge bottleneck. So that way, when we see how this literature is developing in this homomorphic encryption related domain, there are two parallel types of works going on. The first type of work is to develop efficient homomorphic encryption scheme. So here you can see now already one table is given. There are different FHE tools as of now in the library. There are different types of FHE libraries, FHE compilers, and all of them, they are actually adopting some optimizations to improve the performance. On the other hand, but whenever we talk about any optimization, of course, we should consider that we are actually adding some limitation to, and that optimization, some optimization comes with some inherent limitation. So nothing is free, of course. On the other hand, there is another type of research going on in case of application development. Now, why you can argue that when we are having homomorphic encryption and it is giving me the support that you can do additive homomorphism, you can do multiplicative homomorphism. That means in a simpler way, on the ciphertext, I can do encrypted addition. In the ciphertext, I can do encrypted multiplication. So with the concept of universal guess, that means I can develop anything, I can implement any arbitrary algorithm. Of course, this is true theoretically. But where is the problem? The problem can be better explained this few lines from this book, which says it must be emphasized that homomorphy is a theoretical achievement that merely lets us arithmetically add and multiply plain text encapsulated inside the ciphertext. In theory, this allows the execution of any algorithm or complex manipulations, like text replacement or similar. But putting this to practice requires the design of a specific circuit representation for the algorithm at hand. Now, where is the challenge? I can better explain with one simple example. let's consider you are basically trying to translate an algorithm to a homomorphic domain. Whenever you are taking that algorithm, you have some few instruction steps, and those instruction steps, those are consist of some basic instructions and some control loops. Now when you are handling this type of while loop, maybe you have that in your algorithm, that while let's say this some relation while n greater than d or n less than d, something, some conditional checking based on your while loop will execute or stop. If this is the scenario, then your n is encrypted, in your d is encrypted, both are encrypted. So whenever you are doing this comparison, you are getting basically some encrypted result. Now your underlying processor, where you are actually implementing your algorithm, encrypted flow of execution, that is unencrypted. So that is the main challenge. That means your encrypted, unencrypted processor, our traditional processors, whatever it may be, they are not equipped with handling such encrypted loops. So that means the key idea here is whenever we are trying to realize any algorithm in encrypted them, in spite of the fact we have the support of this kind of FHE libraries, we have to again take a closer look, revisit the algorithm, need to make the some representation of the algorithm, and need to optimize such kind of hurdles like loop, and there are many more actually. So in this paper we can get some more idea about it. So all these hurdles we have to optimize separately. So in this direction, and this is a very interesting direction of research, and in our lab, we are also taking two separate applications. One is encrypted database design, and another is encrypted machine learning based application design. Like when you are trying to realize the traditional machine learning algorithms on encrypted data, because that is the requirement. When you are uploading your data on cloud, you are trying to realize, first of all, you are trying to access those, maybe you are trying to apply some SQL type of query on those data to access the data, or you are trying to apply some analytics to get the insight of data. So whenever we are trying to realize them in encrypted domain, basically all this SQL related whatever queries you can think, following the TPCC standard, all the types of queries, select, update, starting from select, update, additional operators like here, like operator, square root, group by, order by, whatever you can think. Traditionally, just which one select, SQL keyword, whatever you use, that you need to revisit, and you need to rewrite them in the context of FHE gates. Basically, you have to think them in terms of some circuit-based representation. So there lies the challenge, and of course with some suitable optimizations that will hold good for your encrypted data execution flow as well as your unencrypted underlying processor. So that way we have implemented this encrypted database framework, and these are few experimental results from our group, and also some machine learning algorithms like KNN, like SVM, and how to realize them on some Ansible learning framework. So these are how we can realize the practical algorithms in encrypted domain, not only at the library level, not only on the bit level or gate level, and the actual practical, real world requirement level, how we can translate the FHE knowledge. But if you go through the tables, whatever I have shared, still you can see that FHE related, still we have managed to do it on some standard databases with some 786 rows, 9 columns. Still, it is taking few minutes for just do one SQL query. So this performance bottleneck is there, and we are trying to sort that out with some FHE support, FPGA support and some GPU support. So in the present research, another direction is that this type of performance bottleneck can be mitigated with some FPGA support, FPGA based cluster support, or GPU based thread related thread level optimization. So if that is possible or not. So for that, the present literature has identified few specific modules that can be offloaded to the FPGA, and then we can actually think of designing some hardware software co-design. Like our application will be in the hardware software side, and some FHE blocks that are mainly responsible for the performance bottleneck that can be offloaded to some custom accelerators like FPGA, and GPU based advantages can be also used. So here are a few existing works from other labs. They are also focusing on this direction, and I can just give you a comparison that how much improvement, if we can go in this direction, how much improvement we can actually achieve. We can actually achieve around 400 homomorphic multiplications per second, and for the same application it was tested, we can actually achieve some 13 times speed up for from highly optimized software. So this is some comparison, and this is some promise that usage of suitable FPGA clusters and GPUs together with our software implementation can actually improve the performance, and we can actually achieve this secure frameworks like secure database framework, secure machine learning frameworks to near to some practical performance. And with that, we can similarly, there are another aspect of searchable encryption. I have mostly talked about fully homomorphic encryption because that is the costliest solution. And where the encryption, this is a faster one, but of course it comes with some limitation that only search operation can be supported. In this direction also, FPGA based cluster and their usage is making a notable contribution. So finally, with all this co-processor design idea, where we can apply this FPGA knowledge, where we can make this meaningful. So one application may be DSSI ACI context or Indian context. Maybe it will be meaningful if we think now revisit the security of our Aadhaar database, because Aadhaar, as we understand it, this is the largest biometric database. So of course, and not only in India, like European Union, US policymakers, they are also, if you see some recent reports, they are also thinking, they are taking this as a priority to protect the national database, and also using this type of homomorphic tools to access and process them in some secure way. So why not India? So this is one possible application where this FHE knowledge can be mapped. And other than that, of course, wherever like medical, like banking solutions, banking servers, biometric repositories, wherever we are thinking of storing and processing critical data, of course this homomorphic encryption or this best solution, this framework can be meaningful. And with the hope of this FPGA based and GPU based, co-processor design, we can achieve some near to practical performance. So this is with this I should wrap up this presentation. Thank you. If you have any questions, so please let me know. I can try to answer your questions.
So thank you, Dr. Ayantika. There are a couple of questions. Of course, people are want to know more. So there is one question: is any bill like GDPR for data protection in India?
See, so far there is some data protection, techniques, but that are the data protection we are considering in storage. Like when my data is stored, that is the solution. But
Right.
this AHV can improve that with the enhance that solution with the supporting storage as well as processing solution. So both are possible.
Yeah, so
That
if
can
we
be
can
evaluated.
say about the bill that is GDPR, what is for EU. I think a personal data protection bill is also there, and it's still in the talk. So yeah. So there is one more question: is fully homomorphic encryption quantum resistant?
Quantum resistant, yes, of course. Fully homomorphic encryption, the library supported, it is based on we have shown the result that is based on TFHE1 library, okay, that is Taurus based library, and based on underlying the RL ring LWE scheme. So that is totally fully, quantum resistant. That is post quantum cryptography based.
So how can we classify our data according to risk, like high, medium, low? How we can? So Zenia, would you like to
That
answer
depends.
this? Oh, okay, Dr.
Yes, okay.
Sorry, Ayantika, Dr. Ayantika, you can.
Yeah, sorry, yeah, sure.
Sorry. Yeah, so there are official pages which give guideline on how to do this. And depending on the company, they choose various systems. So most of them work with a classification between 1 and 4, where 1 would be low, 2 would be medium, 3 would be high, and 4 would be critical. And yeah, I think if you follow the link of the NIST page, which I have on my slides, then you will find also links to pages which help you how to assign data types to criticality. Yeah.
Okay. So there is one question. What is the best encryption algorithm?
Depends on application.
Correct.
Yes. Use case
Yeah.
specific.
Yeah, it depends. I mean, for lightweight, you cannot use normal encryption algorithms, and you have to think about lightweight encryption algorithm. And there also you have to see like what is the gate count, and how much it is. So yes, they definitely depend on the application. And also when we are talking about homomorphic encryption, that also it's based on the applications, right? So yeah. So thank you so much, Jania, and thank you, Dr. Ayantika, for a wonderful presentation and talk. And thank you so much for joining us in Best Practice Meet. So
Thank you
thank you,
as well
audience.
very much.
Thank you, audience, for
Thank
your
you.
constant support and wonderful questions. Thank you.
Bye.